Now we will see some applications of distribution law. I have already discussed what is distribution law and how it gets modified when the solute undergoes association or dissociation in one of the solvents. So what are the applications of distribution law? There are numerous applications and we will just mention some. First one is study of association of a solute. So when a solute undergoes association in one of the solvents in which its concentration is C2, but it is existing as normal molecule in the other solvent where its concentration is C1, then the distribution coefficient is given by K is equal to C1 divided by nth root of C2, where n is the simple molecules which combine to form the associated molecules. For example, if you take benzoic acid exists as dimer in benzene, but it is existing as a monomer in water. So value of N in benzene is 2. Similar is acetic acid when it is getting distributed in the solvents benzene and water. Acetic acid also undergoes dimerization. So in such cases value of N is 2. Second one is study of dissociation of solute. When a solute undergoes dissociation in one of the solvents in which its concentration is C2, but it is existing as a normal molecule in the other solvent where its concentration is C1, then the distribution law gets modified. It is written as K is equal to C1 divided by C2 into 1 minus alpha, where alpha is the degree of dissociation of the solute in the solvent. Knowing the degree of dissociation at one concentration, its value in any other concentration can be calculated, since the value of distribution coefficient is constant at a given temperature. Now third one is solvent extraction. The principle of solvent extraction is based on the principle of distribution of a solute between two immiscible liquids. And usually organic compounds are generally more soluble in organic liquids than in water. This is how organic compounds are extracted from plant extracts. The extract is washed with water and then it is shaken with an organic solvent. The organic compound distributes between the organic layer and the water layer, and usually organic compounds are more soluble in the organic layer, and it can be separated using a separating funnel, and the organic layer on evaporation will give you the organic compound that has gone into the organic layer. Such extractions are more efficient when extraction is carried out with small amount of liquids than using the whole liquid in one lot. This can be demonstrated using an example. Suppose two immiscible liquids are taken, which are ether and water. Now suppose 100 ml of the aqueous solution contains A grams of the organic substance. So we have an organic substance present in 100 ml of aqueous solution. We want to extract the organic compound from the aqueous solution using a solvent. The solvent provided to us is ether. The organic solvent is given to us as ether. And the partition coefficient of the solute between ether and water is known. This partition coefficient of the solute between ether and water, let it be 2. So that is concentration of the solute in ether layer divided by concentration of solute in water layer. Let the value be 2. So the partition coefficient is 2 between ether and water layer. Now the extraction may be carried out by the following ways. First one is, you are provided with 100 ml of ether solvent. And suppose you are extracting the organic substance from the aqueous layer by using the 100 ml of ether solvent completely. So you are using all ether in one lot. So you have added 100 ml of ether to 100 ml of aqueous solution which contains a gram of the organic substance, and you have shaken it. Now after shaking, some of the organic substance will go from the aqueous layer to the organic layer. Now let x gram be the weight of the solute which is extracted in the organic layer. So the amount of the substance left in the aqueous layer will be equal to A minus x grams, because initially you had taken a gram of the organic substance in 100 ml of aqueous solution, and to it you have added 100 ml of ether and shaken. X gram of the organic substance has gone from the water layer to the ether layer, and so remaining substance in the water layer is A minus x grams. So concentration in ether layer is equal to x divided by 100, and concentration in aqueous layer is equal to amount of substance remaining is A minus x, and the volume of aqueous layer is 100. So A minus x divided by 100. But we have said that C ether by C water, the partition coefficient is equal to 2. So we can write C ether by C water is x by 100 divided by A minus x by 100, which is equal to x divided by A minus x, and this is equal to 2. So 2 into A minus x is equal to x. So 2A minus 2x is equal to x, or we have 2A is equal to x plus 2x, that is 3x. So we have x is equal to 2 by 3a. So 2/3 of A has been extracted to the ether layer. Thus 66.66% substance is extracted. Next, we are going to use the ether layer in 2 lots. So using 50 ml portions of ether in 2 installments. So you have taken 100 ml of water, 100 ml you have 100 ml of aqueous layer, and in this you have A grams of organic substance. And you are provided with 100 ml of ether for extraction of this organic substance into the ether layer. But you are not using 100 ml of ether in one lot. First, you have used 50 ml of ether and carried out the extraction and separated it out. Then what is done? The remaining 50 ml of ether is added to the aqueous layer and again carried out the process of separation. This time we can see what is the percentage of substance extracted. So let the substance extracted into the ether layer in first step. So let the mass of substance extracted into the ether layer in first step, that is when you have used only 50 ml of ether, let it be x1. So concentration of ether layer will be x1 mass divided by volume, which is 50. So mass of substance remaining in the aqueous layer. Mass of organic substance in aqueous layer. This will be A minus x1 grams, and concentration in aqueous layer will be equal to mass of the substance, that is A minus x1 divided by volume, which is 100 ml. So we can write C ether divided by C aqueous is equal to x1 divided by 50 divided by A minus x1 divided by 100, and this is equal to 2. So when we rearrange this, we will get x1 divided by 50 into 100 divided by A minus x1 is equal to 2. So this will be 50, this will be 2. 2x1 divided by A minus x1 is equal to 2, or 2x1 is equal to 2 into A minus x1. 2 will get cancelled, or A is equal to x1 plus x1, which is 2x1, or x1 is equal to 1 by 2A. That is, half of A has been extracted when you have used 50 ml of ether. So thus 50% of substance is extracted. Now this is put into the separating funnel, and the ether layer and water layer are separated. Then again the aqueous layer is taken, and to that the remaining 50 ml of ether is added and shaken. Now after the first extract, the mass of substance in aqueous layer, it will be half A, because half of A has already been extracted when in the first step. Let x2 be the substance that is extracted in the second step. Let x2 grams of substance be extracted to ether layer in the second step. So concentration in ether layer is equal to mass, which is x2 divided by volume, 50 ml. Concentration in aqueous layer is equal to half A minus x2, because x2 has gone from the aqueous layer, and volume of aqueous layer is 100 divided by 100. So substituting in the expression C ether by C aqueous is equal to 2, you can get C ether is x2 by 50 divided by A by 2 minus x2 divided by 100. This is equal to 2. This is equal to 2x2 divided by half A minus x2, which is equal to 2, or A minus 2x2 is equal to 2x2, or A is equal to 4x2. Therefore, x2 is equal to A by 4. So in second extract, 25% has been extracted. So totally, using 100 ml in two lots, 50 ml and 50 ml, amount extracted will be x1 plus x2, which is equal to half A plus 1 by 4A, which is equal to 3 by 4A, that is 75% has been extracted. We saw that when we use 100 ml of ether in one lot, only 66.6% has been extracted. Similarly, it can be shown that using 425 ml portions of ether, 80.2% of substance will be extracted. Thus, the process of extraction is more efficient if it is carried out in a number of installments. We can get a general formula which can be derived for calculation of the amount of substance that is left unextracted after a given number of operations. So, for this, let volume of aqueous layer, let it be V ml. Let mass of solute be W grams. Let mass of solute in V ml of water, let it be W grams. The solute is extracted repeatedly with a solvent which is immiscible with water, or the first solvent. It need not be water, two immiscible solvents. So, if V ml of another solvent is used for extraction, small v ml of, let small v ml of another solvent which is immiscible with the first solvent, here I have taken as water, first solvent, be used for extraction. Now let mass of the solute that remains unextracted in the first operation, let it be small W1 grams. That is, small W1 grams is the mass of the substance that is unextracted in the aqueous layer. So, mass of solute extracted in the organic layer, it will be W minus W1. So, initially capital W grams of solute was present in capital V ml of aqueous layer. To that, small V ml of the organic layer was added, and in that process W1 grams of the substance remains unextracted. It is in the aqueous layer. So, the remaining has gone to the organic layer. Remaining is capital W minus W1. And let the ratio of C in the aqueous layer to C in the organic layer, let it be a constant K. So, C in the aqueous layer is W1 mass divided by volume, which is capital V. And concentration in the organic layer is capital W minus W1, which is the mass, divided by volume is small v. This is equal to K. K is the distribution coefficient. So, rearranging, we will get W1 is equal to W into Kv divided by Kv plus small v. Similarly, you are carrying out the second operation, second extraction. The mass of solute that remains unextracted, let it be W2. So, just like we have got an expression for W1, so in the second extraction, the aqueous layer had W1, and to that we have added again small v ml of the organic layer, and we have shaken, and W2 will be given by the expression W2 is equal to W1, which is the mass that is present in the aqueous layer, into Kv divided by Kv plus V. This is just like this expression. Here W, capital W was the mass that was in the aqueous layer, and here small w1 is the mass that is present in the aqueous layer. But W1 is given by capital W into Kv divided by Kv plus V. into kV divided by kV plus V. So this will be equal to W into kV divided by kV plus V the whole square. So W2 is the mass that is remaining unextracted in the aqueous layer in the second operation or second extraction. So after n extractions, after n number of extractions, mass of substance that remain unextracted in the aqueous layer, Wn will be equal to capital W into kV divided by kV plus V raised to n. Because here you can see after second extraction the power was 2. So after n extraction it will be the power of the term in the bracket will be n. From this we can say that when small n is large, that is when number of extraction is large, Wn, that is amount remaining unextracted in the aqueous layer, will be small. And after n extractions, the total volume of solvent used for extraction will be n into small v, because n times you have taken small v ml of the organic solvent. Thus it is better to keep n large and v small for better extraction. To sum up, the efficiency of extraction increases with increase in number of extractions using small volumes of the extracting liquid each time. So that is why you must have done in gravimetry, you are washing the precipitate with small volumes of water, small volumes of the washing liquid, and you are transferring the supernatant liquid. But you are not washing in one lot, you are using small volumes, because extraction using small volumes, repeated extraction using small volumes is more efficient than extracting in one lot.